This video is going to look at eigenvalues and eigenvectors and the application to Leslie matrices. Now we're just going to touch on eigenvalues and eigenvectors. We're not going into a lot of detail because we just want to know enough to be able to apply it to our population matrices for Leslie's. So if we let A be an n by n matrix and X be a non-zero n by 1 matrix such that A times X equals lambda X for some real number lambda, then X is called an eigenvector of A with eigenvalue lambda. Now we touched on that with our last lot of examples where our lambda was represented by our growth rate. Okay, so look back at your last example and you'll see that lambda there. So if we consider a 2 by 2 matrix A, which is 2, 1, 3, 4, I can multiply it by 1, 3, which I'll get 5, 15. 2 times 1 plus 1 times 3 is 5. 3 times 1 plus 4 times 3 is 15. Now I could write that as 5 times 1, 3. So by doing that, I can say that matrix A has an eigenvector X, which is 1, 3, and an eigenvalue lambda, which is equal to 5. So when we're looking here, we have A times X equals lambda X. Okay. Now, using technology is a best way to be able to find out eigenvalues. We are not going to do them by hand. So I'm going to go through how to do it with you on the calculator. The summary is here, so you can look that back up later. But let's go and find the eigenvalues of 2, 1, 3, and 4 on our calculator.
So to calculate the eigenvalue, you go to Menu, Matrix and Vector. You want to go down to Advanced Eigenvalues. Then you insert your matrix. If you've already defined it, you could just put in the variable where it is. We haven't defined it. It's a 2 by 2. Put in our value, so 2, 1, 3, 4. And we get two eigenvalues, 1 and 5.
So from our calculator, we had two eigenvalues, lambda 1, which is 1, and lambda 2, which is 5. Now, eigenvalues of a power matrix are very important. Let A be a square matrix and let n be a positive integer. If x is an eigenvector of A with eigenvalue lambda, then x is an eigenvalue of A to the n with an eigenvalue lambda to the n. Okay, so every Leslie matrix has a unique positive eigenvalue, and this is why we're looking at eigenvalues. The unique positive eigenvalue of a Leslie matrix gives the eventual rate of increase or decrease of the population. So it's going to give us our growth rate. So let's look at this example. Consider the following Leslie matrix L and initial population matrix P0. Find the unique positive eigenvalue of the matrix L. So we can do that by going to our calculators and doing the eigenvalue of L. So let's go and do that.
Now to find our eigenvalue, again, Menu, Matrix at Vector, scroll down to Advanced, choose Eigenvalues, and put in your vector. If you're doing Leslie matrices, chances are you already have that Leslie matrix defined because you've been using it or you're going to use it for other things. So you just put in the variable that you defined it as. But if not, you can just type your matrix into the calculator. And you can see that dominant positive eigenvalue there of 1.2.
So the positive eigenvalue is approximately 1.20. Now, part B, calculate P20 and P21, hence find the rate of increase in the population during the 21st time period and the approximate ratio of the sizes of the three groups. So for this one, P20 is going to be equal to our Leslie matrix to the power of 20 times by our initial population, and P21 is going to be our Leslie matrix to the power of 21 times by initial population. So let's go to our calculators and work that out.
Now to find P of 20 and P of 21, this is when I realised I should have defined my Leslie matrix because I'm using it again. I'm going to cheat. I'm going to copy it from up there. And there is my Leslie matrix. My population, initial population matrix, I'm going to define that. It is a 3 by 1. Put in my values. And now I can go my Leslie matrix to the power of 20 times by my population matrix. And then I can do my Leslie matrix to the power of 21 times by my population matrix. If you do need to add these up, which you do in this question, now's the time where you could copy your values and add them. You could also use matrix methods to add your values. So that's that total, and then for the other one, and there are our two totals. And I made a mistake. Let's try that again. Got the third value incorrect. There we go. So to find our rate of increase, I can then go that second value divided by the first. So my current population divided by my previous population. And it's approximately 1.2.
So from the calculators we have, from our calculator we have, which gave us total populations of 3,059.82 if we add up those ones, and 3,670.68 if we add out our populations of P21. Now our rate of increase is going to be 3670.68 divided by 3059.82, which is approximately 1.20, which was our eigenvalue. So a much quicker way of working out what our growth rate is. Now from this, we have a quite important theorem. Let L be a Leslie matrix such that the unique positive eigenvalue lambda is dominant, then p k plus 1 is going to be approximately lambda 1 times p of k for large k. Now, note it is for large k. These kind of stabilizations, the stable growth rates, don't happen for a while, as we have noticed. So what this is saying is our population in year 50 is going to be equal to approximately lambda times our population in year 49. Okay, so the proportion of the population in each group stabilizes over time, and that's why we can do this. Now, moreover, the eventual age group proportions can be found from the proportions of the entries in the eigenvector x with eigenvalue lambda. Now, a dominant eigenvalue lambda gives valuable information about the behavior of population over time. So instead of calling it the growth rate, we really should call it the rate of increase because it could be decreasing. If lambda is greater than 1, our population is going to be increasing. If lambda is less than 1, our population is going to be decreasing. And if lambda is equal to 1, it means it's stabilizing. Putting that formula in terms of n because of number of years, p of n plus 1 is approximately lambda times p of n.